We are just hearing you now.
Okay, you can hear me well. Okay.
Yeah. We can hear you clearly.
And can you see my screen?
Yes, sir. We can see.
Yes, we
Okay,
can
great.
see.
All right, thank you. Thank you. Okay. Sorry. Sorry about the glitch. So we have to revert to this medium to start with. So once again, my name is Olumide Taiwo is my name, and but for short, you don't need to call my name in full. Just say OT and move on. Okay. So this morning, we're starting with inference making. Everybody is every day of life, every individual, households, organizations, states and nations, everyone is involved in this business of making inferences on a daily basis. In fact, from minute to minute, from hour to hour, everyone is making inference one way or the other. So, so I think as a starting point, we would like to delve into that world, right at the beginning. One of the reasons why it's important to delve into that world at the beginning is that right now, if you look at the world, we are moving towards an era of big data, right? The ability to think data is very, very crucial. Ability to use data, right, for inferences is very important. Understanding what really we're trying to do using data and what we should make of it is really important. Then number two, we also want to be clear that when you talk about making inferences, everything is not data. We have some other areas, right? Everything is not quantitative data, right? In terms of the way we make inferences. In fact, even when you are writing has to be logical. Writing has to flow from one thing to the other, to the next, to the next, to the next. That's even in writing. If you've done analysis, you want to write it down, you have to be very logical the way you present it. So knowing to do analysis is one thing, but knowing to communicate it is another thing. Okay, because you can have a lot of capacity to do a lot of data work and so on and so forth, but if you can't communicate it effectively, that work you've done is not really very useful because people will not understand it. I know that people are these days now visual things here and there, but that's not all. That's not even if you have all the visuals. If you don't present it logically, if you don't have logical presentation of your case will not land, right? Now, so that's why it's important to start with this. I mean, the way you think, I mean, generally, the way people write is the way they think, not the way they talk. You don't write the way you talk, you write the way you think. So the way you think about any subject is what determines the way you write about it, or anything at all. All right. So let's go. So in decision making, it happens daily on the basis of inference. All right? And the inferences are either mathematical or statistical. Okay? So when we say mathematical, I mean deterministic, right? Or it's statistical. And then let's go about this decision a little bit. There are three primary instances under which people can be making decisions. You can make a decision under certainty, okay? Certainty. Under risk or under uncertainty. A lot of people don't know that difference between risk and uncertainty, okay? And when you talk about certainty, risk, or uncertainty, they are actually characters of the outcomes that are dealing with, outcomes of the event you are trying to get into, right? Now, under certainty, when you say you are making decisions under certainty, what it means is that the outcomes and the associated conditions are fully known, and the occurrence of the outcomes, the occurrence of the outcome is guaranteed. For example, if you invest in treasury bills, the government, if the government issues treasury bills and you invest in it, if it's a 30-day bill you invest in, or 9 or 60 days or 90 days, you are very sure that in 30 days or 60 or 90 days, depending on the tenor of your investment, you get your money back and the interest. There is no uncertainty there. There's no risk there. It's certain. Why is it certain? It is because that investment is backed by an institution, government, that is known to exist perpetually, right? That's number one. And number two, known to be the sovereign guarantor of credit. Government is a sovereign guarantor of credit. So the highest level of credit worthiness should be the government of the nation. So when the government is backing an instrument, an instrument, it is certain. I mean, that's why you have the most certainty. So that's one. Under risk, right? There is knowledge of. So now, if you are thinking about decision making under certainty, you use deterministic models, mostly mathematical models. If you are trying to make a decision under risk, decision of risk, there is knowledge of the possible outcomes, but the outcomes can only be guaranteed with known probabilities, right? There's a chance that it will be this outcome or that outcome. If I toss a coin right now, a balanced coin that has a head or a tail, a balanced coin, and not an imbalanced coin, a balanced coin, that's what we say. If I toss a balanced coin, the probability, the possible outcomes are a head or a tail. And the probabilities of being a head or being a tail, as based on experiments is just half, right? So you can come with with head, and a head can be the outcome with probability half, or it could be a tail, probability half. So that's a situation of risk, right? You know the possible outcomes, but you can only guarantee the outcomes with some probabilities that are known. And so if you're making a decision on that risk, you basically use statistical models, right? In terms of finding your way through inference, okay? Now, the third category is when you're making a decision under uncertainty, right? When you talk about being under uncertainty, there is some but incomplete knowledge of the outcomes, right? That's how you know. There is some knowledge which you cannot guarantee is complete. But then there is no information to assign probabilities to them. You cannot assign probabilities, just like assign probabilities to what happens if you toss a coin, or what happens if you roll a dice, that has six sides, because the a balanced dice. You can assign probabilities to them, but there are some instances that you cannot assign probabilities to. You don't fully have the complete knowledge of the outcomes, of the possible outcomes, and then also you don't have any evidence, anything to use in assigning probabilities to them. So in this situation, decision making or inference making basically will rely on learning models. Okay, so in learning models, you have machine learning, you have deterministic learning, you have statistical learning, or whatever it is. So learning models so if you are working on the uncertainty, and when you say uncertainty, it's about the outcomes, right? It's not about the process, it's not about the event, it's the outcome. that determines whether it is a risk, whether it's a certainty, or whether it's uncertainty. Okay, so so that's what we can say for now, at least elementarily. We'll start getting into the midst of that. For example, by the time you start thinking about machine learning and the rest of them, so that's you're getting to more trying to make decisions when you are faced with uncertainties. So in general, on another level, inferences are either deductive, right, or inductive. So when you're making deductive inference, that is based on a general understanding, right, you are making inference for specific cases, okay? But on the inductive side is based on specific instances, right? You're trying to make a decision about a more general case, a more like population-based case. For example, mathematical induction is basically deductive induction. Statistical induction is basically inductive, right? The process, right? Whether you are learning from a general and you're learning from a general and then making inference for a specific situation, or you are learning from a specific cases or a sample, and then you're using the knowledge from the sample to make inferences about the general population. So one is deductive, one is inductive. Okay. So let's start with deductive inference. Okay. So mathematical inferences are deductive inferences, they're deductive. And when you talk about mathematical inferences, mathematical inference rests on drawing logical conclusions from two things. Number one, a set of axioms. When you talk about axioms, you mean some agreed assertions, right? Declarations or statements about the world, about the way the world works, about how our system works, right? Is somebody raising hand there? Let me check. Okay. Badogun, go ahead. Go ahead. Balogun is raising his hand, Abi. Are you speaking or did you put your hands down? Hello? Can anybody hear me?
Yes, we can. I hear you.
Okay, Balogun, go ahead. You raise your hand.
Maybe that's a mistake from his end.
Okay, all right. Okay, so let me just continue. All right. So two things, a set of axioms. I mean, for those of us who have math background, there's like settled, agreed assertions, right? About how the world works. Then, in addition to the axioms, you also have a set of inference rules, right? Like if this then that, if this then that. So, and those rules. What's the question? Can more than one type of model be used at the same time? Well, you can have a system where the output of one model falls into the other one, or the output of this enters the other one, or you can have some kind of hybrid, like hybridization, right? But maybe in the world of learning models, you can have that, like learning models, you can have that. Although, for example, if you are using tools like Python and the rest of them, you'll be having a lot of logical flows in your code. So you can have the use of some of this. But in terms of in terms of the deductive reasoning, you will see that it works differently than inductive reasoning. Okay, I will explain that. Thank you for the question. All right. Okay, so let's continue. Now, so a set of so you have a set of axioms and a set of inference rules that allows us to deduce new assertions from old ones or determine whether a given assertion is valid or not. That's one. So now, in deductive inference, in practice, what we do is that we accept or reject new statements derived from others that have been accepted under mutually agreed conditions, right? So a set of axioms have been everybody accepts that. So, and then based on a set of inference rules, you make new statements, right, from the old ones, and then we can test, we can accept it or reject it. We can test whether we should accept it or we should reject it. Or in another way, we arrive at a particular statement from a more general statement and supporting premises. So now, let me give you an example. If you have a statement that says like all securities backed by government are risk-free, let's say, suppose that's something that all of us agree on the way the world works, that any security backed by government are risk-free. And then we also know that the Nigerian Treasury bill is backed by the government, right? If I give you these two statements, you don't need anybody to tell you anything about Nigerian Treasury bill that it is risk-free. You don't need anyone to tell you that, because from the two you will be able to deduce that the Nigerian Treasury bill is risk-free. Okay, so that's just the way it works. The first statement says that all securities backed, because it's all securities. That word all securities backed by government are risk-free. Then Nigerian's Treasury bill is backed by government, right? It should lead us to infer that the Nigerian Treasury bill is risk-free, essentially. So a lot of people, the way they write, for example, the British people, British and European people, the way they write is that when they want to write, they will give you the premises. They will write premises. Then in the end, they expect you that once you've gone through all the premises, you will see the conclusion, right? You can use the conclusion there. So, but the problem is that if you take them 2 pages, or if you take them a paragraph of, I don't know, a paragraph that's almost 1 full page, right? To put in all the premises, and then get to the end before I see the conclusion. Somebody who is reading that kind of article must have time, right, to go through all the premises, maybe major premises, minor premises, and then to come to the conclusion that the paper is drawing. So the British people, that's how they write, and they've stuck to it over the years. By writing from the New World, that's the North America, for example, they don't write that way. They start from tell us the conclusion. Tell us the conclusion. So tell us what you conclude. If you're interested in your premises, we'll read them. Okay. So you see them that the first line or the first sentence, they'll put it in bold, or they have what they call a controlling sentence or a leading sentence in a paragraph, which is like the conclusion. Then what is left in the paragraph is to explain that conclusion for you. So, so that is, if you think that these things don't show up in the way people write, it's not true. It shows up in the way people write. Just that the New World says, look, we don't have time to go through all that. Just tell us the thing. If you want to see the premises behind it, we will come back to it. Since since you found this conclusion, let's hear it. And let's whether we agree with it or not. If you agree with it, to move on. If you don't agree with it, we can look at your premises to see whether the premises can help us to come to the conclusion that they have come to. Okay? All right. Now, so I said that mathematical statements, right? So it's statements now. So now let's talk about mathematical statements. Okay? A mathematical statement is an assertion or declarative sentence that can be verified and has the property of being true or false. Okay? Okay, that's a mathematical statement. It's an assertion or a declaration that has the property of being true or false. Example, it is cold in this room. It is raining outside. This building is handicap friendly. You can verify whether they are true or they are not true. So if I say it's cold in this room, you just need to check. Bring a thermometer and measure the temperature of this room. Is it cold? If I tell you it's raining outside, just look outside. If it's raining, you know it's raining. So that's when it's true. This building is handicap friendly. Okay, you just go and check. Do they have handicap friendly infrastructure there? Yes, you can verify it. But other things you can say that are not mathematical statements is give me the key. Right? So I wish this class is over now. Or don't jump down, right? So ordinarily, you would think that these things are statements that have the property of being true or false. It's not true. So give me the key. So some people will say, that is showing that somebody is holding a key, right? It is saying that somebody is holding a key. It may not be the case. Somebody may not be holding a key. If you say, give me the key, somebody may not be holding the key. The key can just be resting on the table somewhere. So somebody can be holding it. It can be on the table somewhere, right? It can be in a bag. So just to give me the key, it doesn't tell us something we can prove whether it is right or it is wrong. I wish this class is over now. It's a wish. We don't know when the class started, right? We don't know what's going on in the class. We don't know whether anything is happening in the class. It doesn't convey information that can test and say whether something is true or false, right? Or don't jump down. So you might think that don't jump down means that somebody's trying to jump down. No, a lot of parents they say, hey, don't put your leg there. The child is just sitting down, he's not doing anything, but the parent just say that place is dangerous. Don't put your leg in that place. So it doesn't mean the child is trying to put his leg in that place or trying to jump. They don't necessarily mean so. Those examples are not mathematical statements because they are not conveying they don't have the property of being verified, right? Of being true or being true or false. Their truth or falsity can range from. I mean, it has. They can have there can be a finite and and is it finite or infinite set of possibilities. So they are not mathematical statements. Now, a statement is either true or false, but cannot be both simultaneously. Okay? So every statement is either true or false, but cannot be both at the same time. Now, then in statements, you have a simple statement which contains only one assertion, whereas a compound statement contains two or more simple statements. The two or more simple statements have to be joined by a connective, what we call a connective. Every day you speak every day, you use connectives. And, or, if this, then this. All those, they are all connectives. Okay? So a compound statement has the property of being true or false, depending on the truth or falsity of the component simple statements and the nature of the connectives. Okay? So for a simple statement, just go and check. It's raining outside. I go and look. Is it raining? It's not raining. That statement is false. But if it's a compound statement, for it to be true or false, it depends on whether the simple statements in it are true or false, and also, not just that, the nature of the connectives between them. So, for example, if I say it is cold in this room and it is raining outside, and if I use and to join the two, if either of them is false, that statement is false, right? If at least one of them is false, that statement is false. But if I use or, if I say it is cold in this room or it's raining outside, and if I go outside and it's not raining but it's cold in this room, that statement is true because it takes both of them to be false before that statement can be false, right? So in a compound statement, the property is that it can be true or false depending on the truth or falsity of the component simple statements. Okay, and then not just that, but the nature of the connectives joining them. Now, an argument is a set of statements, including premises and a conclusion. An argument is valid, okay, when the conclusion is true, whenever the premises are true, okay. So, all right, the great debaters, the fallacies are not just to them. So, I don't know if anybody has seen that movie, the Great Debaters, right, by Denzel Washington. At the beginning of it, you see the mechanics of logical thinking, logical reasoning, right? So when he was trying to train those young kids from this downtrodden college in terms of debating, and then led them over from that very local area, led them and trained them, brought them up to know the art of debating, and then they went ahead to sort of actually beat Harvard University many years ago. So you see a lot of syllogism in the discussion. I mean, if you have a chance, you can just watch that video, just the early part of it, right? If you don't want to watch the whole thing, just the early part of it. Okay. So the mechanics of making arguments, premises and conclusions, and so on and so forth. So it's nice if you can take a look at it. So now, why am I talking about this? We are discussing inference making. You have to analyze things. So dealing with mathematical mathematical induction, mathematical inference, you have to do some analysis as well, just as we do analysis in statistical inference. So there is there is symbolic logic, or what we call Boolean or algebra, right, in mathematics. So, in fact, many years ago, this used to be a compulsory course in the first year. It used to be organized in the Department of Philosophy. Everybody should go and attend that class. That used to be the rule. Maybe they've changed it or not. I don't know whether they've changed it or not. But symbolic logic is very critical to reasoning, to thinking, even to writing, actually. Because if you want to write logically, if you want to write in a way that is persuasive, there are ways in which you must organize your writing. Okay. So symbolic logic or Boolean algebra, science of reasoning and analysis that employs formal principles and methods in validating arguments. Okay. Symbolic, because when you are given an argument, what you do that you translate all simple statements and connectives into symbol, right? You've seen that an argument is a collection of statements. Some of them are premises, some of them are major premise, minor premise, and whatever, and some of them are conclusions. So they are statements that are, an argument has a lot of statements, and then they're being connected by different things. Now, so in symbolic logic, you take the argument and you break it down into a set of statements and connectives. The entire argument becomes, you translate everything into symbols. So every statement, you will give them specific letters, right? Symbol, maybe like A to Z or something like that. And every connective, they have their own specific symbols. Connectives include conjunctions, right? And is conjunction. So that's a symbol for, that's inverted V. That's a symbol for and. Disjunction, right? That's the V. That's the or, right? This or that. Then conditionals. If this, then this. That's an arrow with only one direction. Biconditional is arrow in two directions. If and only if, right? This happens if and only if that, or this one if and only if that. So for if and only if, you use a biconditional because it says if and only if, not just if, right? Then join deniers, that is neither this nor that. Neither this nor that. This is that. That is a symbol that you used to connect them. So other symbols include negation. So if you negate it, which changes the truth value of a statement from true to false, or vice versa. So let me just use this very simple example. In this table that we see here, in the first panel, so there are 3 panels here. In the first panel, so I want to use a statement that has only 2 simple statements, P and that we letter P and Q. So P is one statement, Q is one statement. And so now, when you want to do a truth table, that's a truth table. Statements, the number of lines, number of rows of the table should be 2 raised to the power number of simple statements. For example, if there are 3 simple statements, your table will have a length of 2 raised to the power 3. If there are 4 simple statements, the length of the table will be 2 raised to the power 4. So this one has 2 simple statements, so 2 raised to the power 2 is 4. Now, we take the first letter, P, and then Q. So the way you arrange is this: you want to have equal number of truths and false, right? So the first 2 is true, the second 3 is false. Then for Q, you alternate in such a way that you have true, false, okay? True, false. So if there are P, Q, and R, let's say, if there are 3 columns, P, Q, R, okay, P, Q, R, so three simple statements. You have 2 raised to the power 3 rows, right, of truth values. So for P, you start with 4T and 4F. When you get to the next one, you go to 2T, 2F, 2T, 2F. When you go to the last one, you have TF, you have TF, 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 TF. Okay. I hope you are following. Now, as the rule, let's say I want to do P or Q, right? P or Q, right? Which is disjunction. Look at that symbol for disjunction, P or Q. For P or Q, as I said, P or Q, if it is or if the or is a conjunction between 2 statements, it's only false when both statements are false. Okay? So P or Q is false only when P and Q are both false. Otherwise, it is true. I made an example the other time. If you say it is cold in this room and it's raining outside, so if you use and, and it can only be true when both are true. Maybe if you use
Hello,
or,
we can't see your screen again.
you can see my screen. Wow. Okay.
Yeah.
Let me start with.
I can see from my end, though. Maybe it's your network.
Okay. I
Okay.
can see clearly now. I can see clearly now.
Okay. Okay, you can see it now. Okay.
Yeah.
Okay. All right. So P or Q, right? That symbol is or. The V, right? V, like capital V is or. So P or Q is when it is cold in this room, or it's raining outside. Because I said or. As long as any of them is true, that statement will be true. It will be only false when both of them are false, right? When I use or to be the conjunction between them. Now, let's look at another case. That's the second panel. I replicate this again, the P and Q, the first 2 columns of the first table. I repeat the first column, P and Q, so TT, FF, TF, TF. Now, I want to find the truth value of not P or Q, right? I want to find the truth value of not P or Q. So first of all, before I can do that, because I don't have not P yet, I have to create not P, right? So that's why I have to create that 3rd column, not P. So not P, you negate the truth value of P in each of the rows. So when in the first row, P is true, not P should be false, right? P is true, not P should be false. P is F, not P should be true. P is F, not P should be true. So now I have not P and I have Q now. So now I want to do the value of not P or Q. And the rule is this: you look at the column of not P and column of not Q. And not P or Q will be false only when both are false. Okay? And that's the second row, where both are false in the second row. Otherwise, it is true. It is true. Okay? I hope it's clear. Is anybody raising hand? Okay, we can do it later. Let me go to the third one, which is a biconditional. Biconditional. So a biconditional, if and only if this happens, if and only if that happens, right? Or this, if and only if that. So if it is if and only if, that statement is true only when both simple statements have the same truth value. This, if and only if that, is true only when both of them have the same truth value. If they have different truth values, it is not true. So, for example, I repeated P and Q, just like I did in first table and second table, P and Q, TTFF, TFTF. Now, I want to find the value of P biconditional Q, right? So, it's only true when when they have the same truth value. So, when P and Q are both true, it is true. When they are both false, which is in the last row, it is true. But when they have different truth values, it is false. Okay? Right. So these are just simple illustrations, okay? Now, I put an exercise here. Find the truth value of this argument. If you want to find it, this is what you do. There are two simple statements there, P and Q, right? P and Q. So P and Q, just 4 rows, right? P and Q. So you have to build each of the components. For example, you want to build P and Q as brackets and not P, right? You have to get to that column. You have to create that column and that one. Then you have to go and create the second part of it. You have to create, okay, you already have P and Q already created. You have P there. You have, so Q or P, which is also P or Q, right? You have to create P or Q or Q or P and P or Q are the same thing, right? And then you have to negate the value. They have to do P, just like board mass, right? As you are doing board mass, you have to start from inside first. Board mass, brackets of division, multiplication, addition, subtraction. Okay, but here in this one, you start from the inner brackets. You solve the inner brackets first before you solve the outer bracket. So in the end, you have 2 columns, which is the column for the first one on the left and the column for the brace on the right. Brace on the left, brace on the right. A column containing that, a column containing that. Then you do the conditional. So in terms of conditional, the rule for conditional, I'll give you the rule by conditional. The rule for conditional is that a conditional statement is only false when the premise is true and the condition is false. And the conclusion is false. If you have P implies Q, P implies Q is only false when P is true and Q is false. Otherwise, it is true. Okay? So that's the rule of that one. So you can just note it. And there are some resources, some materials you can consult to sort of give you a good idea of truth of symbolic logic. It's very, very important. Why? Because if you want to be a good writer, if you want to write well, you need to have this foundation, symbolic logic. If you want to be able to write well, you need to understand symbolic logic because it helps you organize your thoughts. If you want to write, you don't just pick paper and start writing. I mean, in terms of rewriting, you have to organize your thoughts first. You have to organize them. You know exactly what you want to write. And once you organize your thoughts, you know everything is logical. It flows well. The premise, the conclusion, everything is solid. Everything is set. Then you just start writing. It's like just join those things, join them. If things are in the wrong places, you will know they're in the wrong places, and then you will You sort of shift them around. Being a mathematician, in fact, you are in the best position to write. You should be, mathematicians should be the best of writers, right? Because they are familiar with this world in which, I mean, they know, I mean, there are things you have to put this before that, this before that. So you can't just jump. If you want to make a claim, the claim has to, you have to, if you want to make a proof, there are many ways to make a proof, but you see that it's a very logical way of thinking through it when you're trying to make a proof. The same thing when you are speaking and the logic is not flowing well in your head, you will know it's not flowing well in your head, right? Okay, that's a symbolic logic. Now, you have a chance to sort of maybe some resources we'll share for you to see examples and maybe to practice. Okay. Some people have been exposed to this a little bit, but at least maybe just refresh as a refresher, refresh your mind. I will give examples of practice so that you I mean you become familiar with it. Now, so if I, for example, this example I've given tonight is an argument. And an argument. And in fact, if you want to write the entire argument in words, you can pick two sentences, right? A simple statement, make it Q. B, a simple statement, make it Q. You can rewrite everything in this letter into an argument of words. You can translate it back into word because what we have here is an argument that will translate into symbols. You can retranslate it. Once you tell you what P is and what Q is, you can translate the whole thing back into the argument in words. Okay, so when you have gone to the last column, which contains the truth value of the entire argument, how do we know whether an argument is valid or not valid? Okay, so how do we interpret the analysis of the argument? Some arguments can take you time, real time, to finish analyzing. So if you have a tautology, that is, when the last column, which is your decision column, when it is T or true, then the argument is valid. Okay? The argument is valid. If your decision column reads F or true, the argument is not valid. It's invalid. If it is T everywhere, it is valid. If it is F everywhere, it is invalid. But if it's a mix of T's and F's, right, the argument is not stable. It's unstable, right? It's not stable. There are conditions under which it might be valid. There are conditions under which it might be invalid. Okay? And that's what we call fallacy. In symbolic logic, we call it fallacy. There are many fallacies in the world. Fallacy of composition, for example. In development economics, they say fallacy of composition. That is what works somewhere. The argument that you can easily transplant it into another setting, thinking that it will work, without paying attention to the fundamentals of the place where the thing worked. This is fallacy of composition because you don't know the composition of the system you are drawing from, and the composition of the system you are taking it to. You are assuming that they are the same, which may be wrong. So they say they are committing a fallacy of composition. Okay, so but in symbolic logic language, in the symbolic logic balance, when you have the last column to be T everywhere, that's the tautology. We call it a tautology, not tautology in English language. We call it a tautology. Implies that argument is valid because what you've done is that under a combination of truth and falsity of the simple statements and under the rules of the connectives and all of them, you have considered that argument under all possible scenarios and you found it to be true. So that argument is valid under any scenario, under every scenario. A contradiction is completely false under every scenario you've tried. It's false. But a fallacy is an unstable argument. It's an unstable proposition. It's an unstable proposition or unstable okay, let me continue this argument, unstable argument. In some cases, it might be right. In other cases, it might be wrong. In fact, what mathematicians do mostly in making proofs, they use this last one a lot. Last one. If I can find one instance in which this thing is not valid, then I can tell you that argument is not valid. I can tell you that this doesn't hold. If I can find one instance when it's not hold, that is, if I can find one instance when this thing doesn't hold, I will tell you that that argument is unstable. So we cannot take it as being valid, right? It's unstable. So it's not valid. We are not saying it's completely invalid, though, that it's completely a contradiction. No. We are just saying that we cannot accept it to be true. To be true. Because for it to be true, it has to be a tautology. We cannot accept an argument that's a fallacy as being valid. We cannot accept it. Okay? So in making proofs, right? Sometimes people go through the tautology angle. Sometimes they go through the connection angle. But the fallacy angle is some of the. Sometimes when you see mathematicians making proofs and they are being very tricky, what they are looking for is just to use the fallacy mechanism to quickly defeat to quickly defeat it, the argument. Now, we can also talk about the equivalence of arguments. Okay. When you say two arguments are equivalent, so what do you mean? If these two arguments have the same number of simple statements and therefore they have the same length, right? They have the same length, the truth table is of the same length, right? Two arguments with equal number of simple statements have the same truth value under all logical possibilities. They'll be said to be equivalent. They are equivalent arguments, right? I don't know if you've seen people writing to say this is something, right? They say something, right? And then they say, okay, what I've just said now is equivalent to this. They say it another way, all right? They've said it in one way, then they come back and say it another way and say, what I've said here is equivalent to this one. That is, both of them have the same meaning. Now, that's if they have the same number of simple statements, therefore the length of the truth table is the same. You say that they are equivalent. But also, you can also two arguments with unequal number of simple statements can also be equivalent. Two arguments. They don't have the same number of simple statements. They can be equivalent, right? But what needs to happen is that when you get to the last column, the truth values in the last column must be like must be like a scaling up, right? Of the truth value of the last column of the one with two statements. Let's say one argument has two simple statements, another one has three simple statements, which means that the first argument will have 4 rows in the truth table. The second argument will have 8 rows in its truth table. So for them to be equivalent, if you look at the decision column of the first argument and decision column of second argument, if the first argument has T in its first row, then the first 2 rows of the second argument must be T. If it has F in the second row, the next 2 of the second argument must be F. If it has F in the third row, the next 2 rows, right, must also be the same thing. So just like that the truth values in the last column of the one with 3 simple statements will be like a scaling up, right? Like a doubling of the truth values of this one. They must be arranged that way. If they're not arranged that way, they are not equivalent. The results must come that way. Okay? All right. Okay. Now, for the conditioner, for example, P implies Q, the converse, Q implies P, and the inverse. Okay, so conditional P implies Q. That is, if P, then Q. We talk about the converse, which is Q implies P. That is, if Q, then P. The inverse of that statement is not P implies not Q. And then we talk about the contrapositive, which is not Q implies not P. So you have a conditional statement. We can derive the converse of it. We can derive the inverse of it. We can derive the contrapositive. If you do the check very well, the conditional statement itself and the contrapositive are equivalent. Then the converse and the inverse are also equivalent. All right. Okay. Okay. So that's about what was just the intro into deductive inference. Okay. So we'll find you some maybe on Friday. We'll find you some exercise in addition to this one that that we're given here. Find some exercise to do for you to sort of have a flavor of the truth table. Okay, so and it's critical. It affects the way you think. It affects the way you logically organize your thoughts. It affects the way you argue, the way you come forward with arguments in conversations, the way you understand, the way you organize your thinking, and things you say, and then you are very conscious of it to say, oh no, this no, that this not this no, I mean this is not true. This doesn't necessarily mean the other one, right? And then also in the way you write, the way you organize your writing. So thinking and writing, because you know the way a man thinks, so he is, right? The way you think, that's the way you are. Not the way you talk, the way you think. And so the way you think and organize is the way you write. That's what defines you actually. Okay. So let's go to inductive inference. And a lot of us are familiar with this. We've done statistics before. But let's just talk about it a little bit. So statistical inference is inductive inference. So what does it mean? Okay, so I show you an example of deductive inference in the first slide when I said if you have a statement like all Nigerian and all government-backed securities are risk-free. And I also have a statement that says Nigerian treasury bill is government-backed. Right? You start from all. You have been able to certify that all government-backed securities are risk-free. Right? That's the general. You have that general statement or general understanding, general axiom that have been settled, general thing that have been settled. Now, based on that general thing that have been settled, you are not making inference on just on an element, on a specific element, which is the Nigerian treasury bill. Okay? So if all government-backed treasury bills are risk-free, but Nigerian treasury bill is government-backed, therefore, I can use that knowledge to infer the Nigerian government, Nigerian treasury bill, which is government-backed, is risk-free. So I'm using information from the general, something settled on the general, to make inference on the specific. That's deductive. You can deduce, right? Inductive works in the other way. Inductive inference uses what you find in a selected set. You want to use what you find from the specific set to make inference on the population. That's inductive inference. So you want to use what you find in a limited set or in a very narrow set. You want to use what you find in terms of characteristics to make deductions on the larger set of things, objects or people. That's inductive inference. So you see they are working the opposite ways. Okay. So, and commonly the commonest form inductive inference is a statistical inference. Okay, it's inductive inference. So what happens? You collect a sample, right, from a given population. You don't know. There are some things about the population that you don't know, and you're trying to make inference about it. You collect a sample because you can't measure the entire population for reason of cost, for reason of time. It's too expensive to do. So you get a sample from the population, and then you do your analysis, you do your computations, you do your test, whatever it is, and then based on that, you make an inference on the population. Okay. So that process, so that's why we study statistics, right? So as a science, it deals with collection, organization, characterization, presentation, and analysis of data, and then drawing valid conclusions on the basis of the analysis. Okay. Inductive inference entails the use of statistical models for decision making. And as I said at the beginning, decision making that you use statistics for are decisions under risk, not under uncertainty. Not under certainty. If it's very certain, you don't need statistics, right? In terms of making a decision for it, you don't need statistics. You just write a set of equations and solve them. Now, please pay attention to this. I know a lot of us might have studied statistics, but there are some key things, key understanding that you need to have about statistics. Number one, what is critical in statistics is that we are looking for a distribution. That's what we're looking for. Okay? What you are looking for is a distribution. That distribution is the basis of everything you're trying to do in statistics. So decision making is based on the distribution of outcomes. When I say distribution of outcomes, I mean association of each outcome with the probability of observing it. Each outcome with its probability. When you have a table, a frequency table, right, in statistics, that frequency table is a distribution. That is what we need. That's what we're looking for. That's the basis. That's the starting point of anything you're doing in statistics. Okay, so because when you get that, it's a frequency table. If you divide the frequency by the total frequency, you get probabilities of observing each of them. From that, you can calculate the mean, you can calculate measures of central tendency from the data, you can calculate measures of variation or dispersion, you can calculate measures of shape or cortices or whatever. You can calculate all of them. And then you can go forward and develop a probability distribution you're going to use to sort of make your inferences. We'll get to that in a little bit. I want to explain this clearly so that when you talk about statistics, right? What's it about? What's in terms of decision making, in terms of inference making, get the process. You are focused on the distribution, right? That's what we're looking for, a distribution. And how you can quantify and characterize the distribution, how you can quantify it, and how you will use it, right? To distribution of outcomes. That's what's important. Each outcome and their probabilities of coming out. At the beginning, you see that I said this under risk is made when the outcomes can be identified and you can assign probabilities of observing them. Okay. So what we also do is that we want to estimate a parameter, which means creating new knowledge, right? Or test an hypothesis, that is verifying a conjecture about one or more parameters using the distribution of statistics. So statistics as a science has a definition. Then a statistic is also has its meaning without S. Okay? So statistics as a measure means summary measures derived from sample data. A statistic, singular, a statistic is a summary measure you derive from sample data. But statistics statistics can be is a collection of those measures, those somatic measures. That is in terms of being measures. But statistics as a science, as an area of study, is what I defined in the first part. Okay. So what are we going to do? Information obtained from sample, right? Or if you have a census, used to make inference about the population of objects or subjects. Right? That's basically what we are trying to. But bear in mind, I want you to be thinking distribution. Outcomes. What is this? So in statistics, that's a key thing. That's a central thing. Okay. Now, there are three parts in making statistical inference. Three parts you need to go through. First of all, there is a part that is descriptive, right? So in your descriptive statistics, you want to characterize the distribution. You want to characterize the distribution. You want to find the distribution and characterize it. Distribution of observations in the sample, or distribution of the sample data, right? So the sample you have, what does it look like? Right? What does it look like? Then, when you understand what it looks like, then you come to probability theory, or some call it distribution theory, right? Where we develop the basis for inference from data. Okay, we always say is that based on the nature of the population, what's the best way to use the sample in making inference about that population? That's what we do in probability theory. Then the third part, after you have built the basis in probability theory, then you use sample data and the probability theory to test hypotheses, claims, or statements. You test them based on the sample. Right? Using the sample, what can we say about the population? So the three specific parts of statistical inference, before you can get to that part, you have to do the descriptives, you have to do the probability theory, or distribution theory, then you come to the inferential component, inferential part of it. Okay. So for example, there is some people try to discriminate between probability and statistics, right? So you see this thing there, you can see a sort of a bucket on the left, and then you pick something in your hand out of that bucket. So probability is asking, given the information in the pail, in this pail, what's in your hand? So given the information in that pail, so what's in your hand? So now, statistics on the other hand says that that's statistical inference. Given the information in your hand, what's in the pail? You tend to use a sample to sort of pick out to sort of make inference on the population. All right. So the first part, the descriptive statistics, as I said, you want to characterize the distribution of sample data, and there are different measures that you look for. There are measures of central tendency or center of gravity, or measures of average. We call them different things. Measures of central tendency, measures of average, measures of gravity. So, and on those ones, you have mean, okay, or quantitative average. Now, depending on the nature of the observations, if you are dealing with scalars, right, you talk about arithmetic mean. If you are dealing with vectors and ratio variables, you talk about harmonic mean. If you're dealing with if you're dealing with flow variables, you do that geometric mean. Then also we have quadratic mean. So when you say mean, you have to be specific. Which mean are you talking about? Depending on the nature of the variable you are dealing with. If it's a scalar, we know scalars are quantities that only have magnitude, no direction. That's all. So just arithmetic mean, whatever it is. But if they are vectors, harmonic mean. If you have vectors and ratio variables, harmonic mean. If they are flow variables, geometric mean. Then you also have a quadratic mean, right? There. You also have median or positional average. So mean is quantitative average. Median is positional average. Mode is prominence average. Okay, they are averages. Now, see, when you see people speaking in society, and if you look at the mean or on average, somebody will be talking about voters preferences, right? Talking about the average voter. What does it mean? It's talking about the median voter. Median voter, that's what it's talking about. The median voter in terms of preferences. Voters have preferences that range from some negative to from left to right, right? Like a continuum of preferences, of interest, of whatever it is. So the average voter is a median voter. So a lot of times when people are campaigning, they are focused on the median voter, right? In well-developed electoral systems, they are focused on the median voter. So we say the average voter. You're not talking about the mean voter or the modal voter. You're talking about median voter. That's what that's what to focus on. There are instances when you use the word average. When you see average being used, you have to ask the question: is it quantitative average? Is it positional average? Or is it prominence average? For instance, if you're in a class and there are desks of several sizes, right, in a school, and you say, on average, the tables I found here, on average, they are of this type. What are they talking about? They're talking about the mode, right? You look at the tables in the place, you just a distribution, and you find that in terms of the average table I found, on average, the tables there are of this length. You are talking about the mode because it's many tables there and there. That in terms of just looking at it, you're not talking about the average. Sorry, maybe that's a good example. Let me see. So when you're using the mode, right? When you use the mode, because you can talk about the average length of the table, which is a quantitative average. Yeah, yeah. So you can use the modal or prominence average. For example, if you are talking about the color of the hair, right? Let's say, or maybe color of the eyes, right? Color of the eyes. So you have a set of people, maybe people that attend a particular school, and you're talking about the color of the eyes. So on average, that is the mode, because you can't average out colors, right? You can't say color this plus color this plus color this plus color this divided by number of colors. You get that's something. That's the quantitative average, right? So, but what you can say is that on average, the average person in that school, you are saying the mode, you are saying the mode, right? The average person in that school is blue-eyed, right? Or black-eyed, blue-eyed, right? So that's like a mode. So we use the word average in several instances, but you have to be able to quantify which average you're talking about. You can have somebody talking about an average that if you think it's just mean and talking about, you miss the point. You might be talking about the median or the mode, but they are all averages. They are measures of gravity, measures of central tendency of the data. Now, measures of central tendency, you can also have measures of spread or dispersion. Then you can talk about the range, interquartile range, mean deviation, range, interquartile range, mean deviation, mean absolute deviation, variance, standard deviation, coefficient of variation, and so on and so forth. I can tell you the story of how these things came to be, from range to the coefficient of variation. I can tell you the story, how they started, when they started thinking statistics, how they started from range. The way I arrange them is the way they emerge in the history of statistics. Okay. You also have measures of partition, right? You also have measures of partition or non-central locations, also known as quantiles, right? So you have quartiles, values that divide the sample into 4 equal parts. You have deciles that divide the sample into 10 equal parts. You have percentiles that divide the sample into 100 equal parts, and so on and so forth. You also have measures of shape. Measures of shape. They are also non-central moments, right? Moments, skewness or symmetry, and then cortices, right? In terms of describing the distribution. All these are still describing the distribution. So if somebody asks you about a distribution, And you cannot say a lot about this. You have to be able to give people some insights into the discipline you have, right? The basis of which you are making these decisions. Sometimes I'm kind of I'm surprised a lot of times, and it gives me a pause when I see a lot of papers people write here, especially especially those study economics. You see them writing papers, and they will just tell the story a bit. Then they will tell you there's a model that they want to run, and then they will show you the results. From my perspective, that's fraud. It's because anybody can write anything he likes. There's room for fraud, and truly, a lot of things you see that people say called research here, they are fraudulent. They are fraudulent. They are made up. I'm not making this up. It's a report. It's a report that I've seen that a lot of people that do research around here, they just make things up. It's fraud. a good research article. Before you say you want to show me your results, first of all, show me your data. Let's look into your data. Let's look into the moments. Let's look into all these measures. Just describe it for me. Describe the measures of central tendency, describe the measures of dispersion, measures of partition, measures of shape. Let me see the shape of the distribution, whatever it is. Before you say you want to take data into regression, blah, 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 blah. Because of that, a lot of things that people produce around here and say they've done regression, they're just useless. They are useless and meaningless. They didn't have value at all. Because the basis of what they're doing, you don't even know what data that they're analyzing, you can't see it. Right? You can't see it. You can't see a description of the data. Where a good research article has to start with a description. This is data I want to analyze. And why do I want to do all the regression, blah, 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 that I want to do? I have to explain it. So that's proper research. For you start with a description of the data, right? Central tendency, dispersion, partitions, shape, whatever it is. Because all these regression models, they have assumptions in them. So if your data deviates a lot from the assumptions, you're just bringing out nonsense. Right? Just nonsense. But a lot of people that don't know that those are nonsense, they will think that there's a value inside it, right? But there's no serious value in it, because most of the assumptions on the line is they've been violated, because we can't even see the data you're running. Okay, so that's one. Then so discrete statistics, you have mean, all the formulas are here, variance, so standard deviation, skewness, and cortices, and so on and so forth. So you have all that. Now, the second part is probability theory. I won't say much about that one for now. So it just provide the basis for the science of statistical information data. It builds the structure or framework for using the data you have for inference. Okay, that's probability theory or distribution theory. Then the last part is the inferential statistics, when you use sample data and probability theory to test your claims, to predict this, to test, to tell statements and claims, to test them. So the way you use truth table in deductive reasoning is the same way you use test of hypothesis in inductive reasoning, okay? In statistical inference. What you do when you're doing test of hypothesis is the same thing, it's a similar thing you do when you use truth tables to verify the truth or falsity of an argument. Okay, it's similar in terms of concept. Consider that's there. So you're doing similar things. So the end of it is that you test, right? You test a claim, you test an argument, you test it based on the data, based on the sample, and based on the distribution theory that you have established. You test. Okay, so I don't want to go beyond this point. Otherwise, I'll be it will become too heavy, right, for this introductory class. But essentially, I just want to introduce you to the world of inference. One, deductive inference, inductive inference. And there are situations under which you are trying to make decisions. If you certainty, if you're uncertainty, if you're under certainty, use deterministic models. You don't need any kind of stochastic model, right? You don't need any kind of, just use deterministic model. If government treasury bills, they tell you the interest rate I want to pay you over this period of time. There is nothing stochastic in it. That's what you get. Okay, nothing stochastic. Somebody's running stochastic. There's somebody that like to talk about big things, stochastic, blah 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 blah, all these things. It doesn't apply to things you are doing that are deterministic, where you have this certainty. Now, if there's uncertainty, that into element of risk into it, that's why you do statistical inference, right? And you can talk about all your stochastic modeling and so on and so forth. But then you face a decision of uncertainty, not risk, but uncertainty. So that a lot of learning has to happen. And that's where you have these advances in machine learning, right? Some of them have statistical learning, some of them mathematical learning, whatever it is, different things. Now they have gone ahead. Now you have all these AI tools, all these things, they are all based on learning, right? Learning. When you gather a bunch of data of people, of patients in a hospital, you have some measures about them, their height, their age, their weight, all of them, and then the kind of disease that they are diagnosed for, blah 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 blah. And then okay, so you want to find out. Suppose a person like this shows up at their facility, what's likely to be the person's problem based on these characteristics, right? So machine learning, based on the knowledge that you have fed it with, based on the data you have fed it with, we probably give you a prediction, right? So it's not something you can do easily on that, because it takes a lot to do that. You can't do them easily on that, whether as a in statistical inference, no. Even if we generate probabilities, all that, they are you can use machine learning stuff to generate probabilities for all the possible outcomes. You have to be able to identify all the possible outcomes and generate probabilities. And then, so if you want to come back and do statistical inference, fine, you can do that. Just like somebody asked a question whether you can use a combination of the methods. So if you want to solve the problem in terms of, you want to convert a situation of uncertainty into a situation under risk, right? So which means that you have to use the learning instruments to generate the outcomes, the exhaustive outcomes, and also the probabilities of each of the outcomes. And then you can come back and do your inductive analysis in terms of inferential statistics. Okay, so I'll stop here for today. So, and as I said, the reason why this is essential is that anybody who's going to think about research, anybody who's thinking about being able to do research and write well and do data analysis and so on and so forth, this is an important starting point. You have to be able to understand symbolic logic, not just because you want to be a mathematician, but because you want to be able to, in terms of reasoning, in terms of logical flow of things, in terms of logic, you want to be there, right? A lot of people just think porously. They just think here and there, things just fly up and down. They can't really gather their thoughts together. They can't really, they don't think like they have a framework, right, for thinking, and a logical box somewhere that's generating the thoughts, and they are organizing it. They're here, all over the map, here and there, here and there. There is nothing. They can talk to you for 5 minutes, and you can't even get any. You can't even get anything they're saying. You can't even say there's any conclusion you're taking from what they're saying, because that's where they are. They don't have any. They don't understand anything about logic, the biological organization of their thoughts. They're nothing. So and the world is filled with people like that. So we shouldn't contribute to that. We should probably reduce that population, and then we should be able to think logically. So we'll give examples and problems to solve under this symbolic logic, and then. But the reason why I'm not giving you some problems to solve in statistics, because a lot of you have done statistics, basically. I think in the schools, if somebody say I've not done statistics, I don't know if somebody here that hasn't done statistics at all. But this is just trying to some of that. But that other parts, model logic, is what we think that a lot of people have not come across. Okay? All right. Over. So if there are questions, please, you can raise your hand to ask. Any questions? Can anybody hear me?
Yes, we can hear
Okay.
you.
Okay, thank you. Yeah,
I can hear
so,
you too.
okay. Balogun, go ahead. Balogun, go ahead. Can you hear me? Yes, you get the slides. Yeah. Any questions? Hello? Okay. Maybe there's some question. Jaffa?
Okay, thank you very much for your presentation. And if there's any question, you can be sent admit email or put it on our platform. Thank you very much for joining us. See you next Wednesday. On Wednesday. Okay.
Okay. Ibrahimji, go ahead. Hold on, please. Ibrahimji, go ahead. Ibrahimji, unmute yourself
Okay.
and go ahead.
Hello. Can you hear me clearly
Yeah.
now?
Yeah.
So
Yeah.
I'm
Go
actually
ahead.
looking into a problem. Thank you for the wonderful presentation, and we really appreciate your effort so far. And in fact, I really understood most of the explanations that you have made. I can really see the application of what you have even explained a lot. That in fact, in the kind of judgment areas too, because last year there were I had a denial last year, and I see so many interpretation of the logic that you have explained. I see so many of the things that is one of the reasons why you get to these embassies, and so many people will just have a kind of denial because they look through a whole lot of the definition of so many things that you have defined to have accumulated. So at the end of the day, they see a whole lot of jargons that might not even relate, and they make a kind of deduction from there, a kind of conclusion, jump into conclusion because of so many gaps that they've seen in this thing. So basically, the reasons I'm taking this course is number one, I'm looking into application of machine learning into earthquake in my course. I'm really looking into US PhD program in US. So that's actually the
Awesome.
intention of my taking this course. I've
Okay.
started machine learning on my own parts. Then I started with Python, though I'm a software engineer, but majorly I understood the back end part of the programming language. So I've not been really into this the interpretation and the analysis of data. So it's awesome, and I really enjoyed the whole lot of your presentation. So I really thank you. So one of this thing now is I'm looking at in this program. Are we going to be
Can I hear you? Lost?
applying
Is it
Python
me?
language so that we'll prepare myself for the challenge coming upward? Yeah. I said, are we going to be applying Python or the soft tools that we are going to make use of? I mean, so that I would prepare myself ahead of the
Okay. Yeah. I think yes, you will. Yeah, you will. You will.